Okay, with these in mind, we can now take a look at some examples. You know we have two conditions that we must observe. One is the net force has to equal to 0. The second is the net torque has to equal to 0. Let's look at case 1. In this particular case, the second condition, that is the net torque equal to 0, is already automatically satisfied. You don't have to do any serious calculation. You can tell that it is already satisfied. How do I know that? Well, let's see now. You see this from this example what I mean. Suppose I have a weight dangling there, mass m. Okay, and I'm going to support this weight with a structure like that. 3 strings, 1, 2, and 3. You notice that these 3 strings tie a knot here. Okay, that's just the point. That's just the point. There's no mass here. That's the point. Take a look at what happens at that point. You got 3 forces, right? F1, F2, and F3, right? You know I can use any point, as I learned before, any point as my observation point. As long as the force, the torque about this point is 0, the torque about any other point must also be 0, right? Why don't I choose this point, the junction where all these 3 ropes meet, to serve as the observation point? Because when I do that, I find that since F1 passes through that point, what's the lever arm produced by F1? We recall lever arm is the distance between a force and the point of interest, right? The vertical distance. That is the lever arm output. And that's obviously 0 because that point is right on the force. So F1 produces no lever arm, and therefore the torque is 0. So is F2, and so is F3. So none of these 3 forces provide any torque, and therefore the net torque on point O is already 0, regardless of the values of F1, F2, and F3. It's because they happen to pass through the same point. Okay, and since it is 0, the torque is 0 about this point, must be 0 anywhere else. So that is why I say the second condition is already met. I only have to worry about the first condition, and that is the net force has to be equal to 0. Now, let me find F1, F2, and F3 if I know that this hanging mass has a mass m. That is relatively trivial now, because I only have to balance the force. You know, the weight is mg, okay? The weight of this thing is mg. And to balance it, F3 must equal to mg, right? F3 must be equal to mg. So that's clear. F3 equals mg. And secondly, let me find F1 and F2. The net force is equal to 0, both horizontally and vertically. Let's choose an axis. This is horizontal, and that one is vertical. Let's call this of course is beta, and this is alpha. In the horizontal direction, I have F2 going this way with a horizontal component, and that would be F2 times cosine beta. Okay, so F2 cosine beta. Also, F1 has a horizontal component, but that's along the negative x direction, therefore it's negative, minus F1 times what? Well, the angle here is alpha, so it's cosine alpha. Now that is the sum of the x components or horizontal components of F2 and F1. Okay, F3 has no x component, so that's it. That is the net force along the x direction. That has to equal to 0. That gives you one equation. Same thing happens in the vertical direction. The net force has to equal to 0. Now I have F1 sine alpha going up and F2 sine beta also going up. So both are positive because upward direction is chosen as positive. So F1 sine alpha plus F2 sine beta. Those are the 2 upward components. Now F3 has a downward component, and how much is that equal to? Well, mg of course. So minus mg, minus because it's downward. That equals 0 as well. That gives us a pair of equations, F1 for F1 and for F2. So we can easily solve them. And after some algebra, you find that F1 equals to mg divided by sine alpha plus cosine alpha times tangent beta. And of course, once you know F1, you know F2 and F1 are symmetrical from these 2 equations. So for F2, all you have to do is replace alpha with beta and beta with alpha. You will get F2. In particular, you notice that if both alpha and beta are equal to 0, okay, then we'll be in trouble. Because the denominator would be 0. Sine alpha, tangent beta both equal to 0. So F1 has to be infinity. And that makes sense because what you have now is a horizontal force F1 and a horizontal force F2. How do these two horizontal forces possibly cancel with a downward force F3? That's not possible unless both are equal to infinity. Okay, so that special case certainly is valid. And you can also look at the case when one of the angles is equal to 0, or both angles are equal to 0. Even better, when both angles are equal to 0, things becomes very clear because you just have two forces, F1 and F2, both pointing upwards. You will find in that case that when F1 and F2 are added together, you just get F3. That's just obvious when you look at the case when alpha beta are both equal to 0. Okay, now let's look at another case. This example appears in pretty much every single textbook at this level. It's a very typical problem. If we know how to solve this problem in and out, we pretty much know how to solve all the other problems in this chapter. This is another case which is more comprehensive because it involves considerations of both net torque and net force. There's no guarantee that net torque is equal to 0 anymore, so we have to specifically write it down to make sure that happens. What we have here is a bar, a uniform bar of certain weight. Since it's uniform, the center of mass is right in the middle. The bar extends from C to B. At point C, there's a hinge. Okay, you know what a hinge is, so the bar can rotate freely about this hinge. A hinge can provide both a horizontal and a vertical force. And if you only have that force from the hinge, you know the bar is going to rotate. To prevent it from rotation, I use a cable connecting the bar from point B to point A on the wall. Okay, in the angle the cable makes with the horizontal bar is theta. Suppose I know the weight of the bar, which is mg. Okay, so I have a force here, mg. You notice I'm using a single force located at the center of gravity to replace the gravitational force, extended gravitational force on the object. If that is the case, I have a couple of questions. I want to know what is the tension in the cable. And I also want to know what is the force of support provided by the wall through the hinge on that bar. Okay, please do not automatically make assumption about the direction of this force at the hinge. As a matter of fact, as you will see, it is neither purely horizontal nor purely vertical. It has both components. But there is a force here. Now, let's see. There is a force of support at point C. But we don't know exactly what it is. We're going to try to find it out. Is it possible, before we even find out the supporting force here, that we can first find the force of tension T here? Well, to do so requires an equation which does not contain any force at point C. You know there is a force here, there's no question about it, of unknown direction, unknown magnitude so far. Yet we don't want it to appear in our equation. How does one do that? Well, you recall the keyword flexibility? Okay, flexibility in choosing the observation point. What observation point? Well, basically that's a point about which I apply the torque theorem, right? The net torque has to be equal to 0. I can apply that net torque equal to 0 equation to any point, point A, point B, point C, any point I want. But not all points are created equal. Some points are easier than others to apply. In this particular case, what do you think is the smartest point to apply the torque theorem to? Now remember, I want to eliminate any force about point C. Force is not equal to 0, but the torque of those forces at point C can be 0 as long as they don't have any lever arm about a certain point, right? Okay, so those forces have no lever arm about what point? Yeah, about point C, because they go right through point C. Okay, so what is the best thing to do if I just want to know the tension? using only one equation to get it, is let me apply the torque theorem about point C, because that way I don't care what force the hinge gives to the bar at point C. That force, whatever it is, has no lever arm about point C, therefore it disappears in my equation. So let me find the net torque about point C. Okay, don't worry about that force. I only have two torques, one from the gravitational force, the other from the tension. Okay, let us choose the clockwise direction as positive, so therefore this torque is positive and that torque, being counterclockwise, is negative. Let's say the length of the bar is L. So from here to there, that's L over 2, right? L over 2. So what is the torque provided by mg? That would be equal to mg times the lever arm, which is L over 2. And that's a positive torque. Now, minus the torque provided by tension. That should be equal to 0, because the net torque about point C is equal to 0, just like the net torque about any other point. Okay, you must then find out the lever arm of this tension T measured from point C, right? How do we do that? Well, we start from point C, we drop a perpendicular, that's how we find the lever arm, to the line of action of the tension T, that's the line of action. That is the lever arm, okay? That's the lever arm. Now, this length is L, this angle is theta, and here is 90 degrees. So R perp equals to L times what? Sine theta, isn't it? Right? L times sine theta. Okay, so there we go. We have tension times sine theta times L. L times sine theta, that's the lever arm, and then times tension. Now that sums up to 0. Okay, the net torque about point C is equal to 0. And that single equation immediately tells us what T is. So what's T? T equals, you just TL sine theta equals mgl over 2. So that is just mg over 2 sine theta. That's it. Okay, we found the tension. One step. You know, that is not the only way to find the tension. There are other things you can do. You can apply the torque theorem about point A, point center of mass, point B, whatever. You can find the tension eventually. But the problem is, you're not going to find the tension with a single equation alone. This is the only way for you to find T with a single equation. Because this is the only point, C, through which, when you apply the torque theorem, you can ignore any force here, because they have no lever arm. Otherwise, we're going to have to deal with the force about point C, which we do not know. So a single equation will not do it. Okay, having found tension, we're now ready to find the supporting force at point C. Now, remember I said this force has both horizontal and vertical component. How do I know that for sure? Well, first of all, let's see what kind of horizontal component it must have. Should it point to the right or to the left? Well, there are a couple of things we can do to check that out. Well, first of all, if you know the net force about the bar has to be equal to 0, right? Now the bar is subject to several forces. There's a force here, there's a force here, there's a force here. But let's look at the horizontal direction. Okay, let's look at the horizontal direction. mg has no horizontal component. T has a horizontal component going left. And the only horizontal component that can cancel with that is the force, horizontal force about on the bar at point C. So there has to be a horizontal component going to the right to cancel with it. Okay, so at point C, you must have a force going this way. Let me call this F1, okay, F1. It has to go this way. As a matter of fact, this is not the only way to make sure that the force, the horizontal force at point C has to be pointing to the right. There are other ways to guarantee that. For example, I can apply torque theorem about point A. Okay, I'm not really going to do it, but suppose I did. Without even writing down the equation, you know roughly what's going to happen. If you apply torque theorem about point A, the tension has no lever arm because it goes right through it. Okay, and the whatever vertical force about at point C also has no lever arm because it also goes right through it. There are only two forces left that do provide a torque about point A. One is mg, and that's a clockwise torque. in order to make sure the torque about point A is 0, there has to be a counterclockwise torque somewhere, right? And where does it happen? Well, only remaining point C. Point C is subject to a horizontal force which has to provide a counterclockwise torque. So you see, that is why the force has to point this way, because that's the only way to provide a counterclockwise torque. If it points that way, that's a clockwise torque again, so that cannot cancel with the torque of mg. So no matter how you look at it, there is a force, horizontal force, pointing this way. Okay, F1. I don't know what it is, but it has to point this way. Next, let's look at the vertical component. I say there also has to be a vertical component. How do I know that? Well, for example, we can look at the torque about mg. Okay, you know the net torque about mg also has to equal to 0. About mg, I'm sorry, about the center of gravity, that is. mg has no torque, right? The tension has a counterclockwise torque about that point, right? F1 has no torque because F1 goes right through it, you see? Okay, so who is providing a clockwise torque that cancels the counterclockwise torque of the tension? There has to be a vertical force at point C, and it has to point upwards, and that's how you provide a clockwise torque, which cancels the counterclockwise torque of the tension. So we notice there has to be F2 as well, which is upward, okay, upward. So we need to know both F1 and F2 to get the whole picture, to get the net force exerted at point C on the bar. How does one find F1 and F2? Again, there are multiple ways of doing that. You can use force equation and torque equation. The thing is, we already know what T is, okay? We already know what T is. Since we know what T is, and only two forces are horizontal. One is the horizontal component of the tension, the other is F1, right? And they must cancel each other out. That gives us the most direct way of finding F1. Okay, so we demand that the net force along the x direction on the bar be equal to 0. If you choose this as the positive direction, positive x direction, F1 is positive. And the only other force exerted on the bar that is horizontal will be the horizontal component of T, and that is T times cosine theta, negative, pointing that way. So minus T cosine theta. Now that has to equal to 0. This is the easiest thing to do to find F1 because I know what T is already. Okay, I know what T is. So we find that F1 must be equal to T times cosine theta. T is right here. Okay, so the answer finally is mg over 2. And there's a cosine theta, there's a sine theta. You flip that cosine theta, cosine theta down. That is, you sine theta, you cosine theta divide sine theta, you get tangent theta here. Okay, that is F1. That is F1. And you notice, interestingly, that when theta equals 0, F1 is in trouble. F1 has to go to infinity. And that sort of you think about it, that actually makes sense. Because now you are pulling the cable is this way. Okay, when you pull the cable this way, how do you possibly prevent this thing from falling, from sliding, rotating this way? You must use an enormous amount of tension here, right? And that requires an enormous F1 to counteract with it. So it actually also makes sense. But I want to show you that there are indeed more than one way to find F1. What I showed you was perhaps the easiest way to find F1. But that's not the only way. What I can also do, like I just said, is to use the torque at point A. Okay, so let's use the torque about point A. If you look at the torque about point A, you know the net torque has to equal to 0. So torque A has to equal to 0. Tension has no torque, F2 has no torque, F1 does have a torque, and that's a counterclockwise torque. Let's say that's a positive torque. Okay, we call it positive. So F1 times the lever arm, this is the lever arm right here. Now, how much is that? This is L, this angle is theta, so that distance from A to C, isn't that L tangent theta? Right? Okay, that is a counterclockwise torque. Who gives you the clockwise torque? about point A? Well, that would be mg, okay? That would be mg. So how much is that? That will be minus, because it's clockwise, mg times the lever arm. What's the lever arm? Well, here is the line of action of mg. You drop a perpendicular, okay? So what do you get? You get just half of L, right? L over 2. Now, that also equals 0. And what do I get? I find that F1 equals L and L cancels. You get mg over 2 tangent theta. Of course, that answer is the same as before. Okay? It's the same as before, as right here. The method is different. The first method demanded the net force on the x direction be equal to 0. The second method demanded that the torque about point A be equal to 0. I'm getting the exact same answer. As a matter of fact, the second method has an advantage, the second method, in the sense that in doing so, we don't have to know what t is, you know, right? We don't have to know what t is. In the first method, you have to know what t is. But, you know, the reason why we can get these different methods is because we can apply both torque and force equal to 0 equation. And not only so, the torque equal to 0 equation, you can apply to any point, point A, B, C, whatever. Again, that's the key word, flexibility. So utilize it to the best of your advantage. Okay, the only thing left is to find F2. Okay, to find F2. So I'm pretty sure at this point you know very well how to find F2 now. There are, again, you know, a couple of ways you can do that. One is to demand the net vertical force be equal to 0, right? So you have F2, you got T, what's that, T sine theta going up, right? And you got mg going down. They must cancel out. So F2 plus T sine theta must equal to mg. That will tell you what F2 is. Okay, so let's write it down. So you got F2 plus T sine theta minus mg has to equal to 0. Okay, I know what T is. T is mg over 2 sine theta. Okay, mg over 2 sine theta. So I found F2 to be equal to mg minus T sine theta, which is mg minus mg over 2 sine theta times sine theta. So mg over 2 sine theta times sine theta. You know the 2 sine thetas cancel. The second term is just mg over 2. Okay, so the answer is just half of mg. F2 is always half of mg. That came from the fact that the net force in the vertical direction on the bar has to equal to 0. Okay, but you know that automatically comes from another consideration, and that is the net torque. Okay, the net torque about point B has to equal to 0. Okay, it is not wise to use point C or point A anymore. Why? Because if you choose point C or point A, the lever arm of F2 is automatically equal to 0, so F2 will never appear in those equations, so it's useless. Using point B, however, gives the simplest answer. First of all, don't worry about T. T goes right through it. The only counterclockwise torque is from mg. The only clockwise torque is from F2. You see that? Okay. mg has a lever arm which is half of L. F2 has a lever arm which is 1L. That's twice the lever arm as mg. So therefore, F2 is half of mg. It's simple as that. Okay, let me write it down. F2 times L, lever arm. I'm choosing clockwise direction as positive this time. Minus the counterclockwise torque at point B due to mg. So minus mg L over 2 equals 0. Okay. By the way, this is the sum of the torque about point B. And that gives you exactly the same thing, F2 equals mg over 2. Okay, so please make sure you know this problem, how to do it inside and out, not only using just one method. I want you to try all these different methods. Okay, talk about point C, point A, point B, net force equal to 0 horizontally, net force equal to 0 vertically, and I want you to compare notes to see which method is more efficient, is easier. They all give you the same result, but which method is easier and why? Once you know that, the next time you see a different geometry, you will know which method is the best approach, which method gives you the easiest answer. As I said, for example, using point C is the best choice if we don't want to mess with F1 and F2. We don't know them yet. Then the easier thing to do is to use the torque about point C, because that automatically eliminates F1 and F2, these two unknowns, from your equation. Okay, so that is a very typical problem of great importance.